This recording will be made available on Monday, so you can come back to it and you can dig into it. And if anyone asks in the chat, please just remind them that it'll be up on Monday. This notebook is not shared yet. It will be shared tomorrow, and it will be shared on the canopy or crop competition, which I've just put in the chat. So I'll keep posting this link. If you sign up for this competition, you'll find the resources and webinar from 2 weeks ago. And then tomorrow you'll find this notebook. So the reason we've done that is so that you listen hard and you don't get distracted yourself. This is a 3-part webinar series. This is webinar 2. It's on processing Earth observation data for machine learning. Brilliant. We know about satellites. Now what the heck do we do with it? And that's what this webinar is about. I'm going to hand over to Corey from Amini, who's currently sharing his screen, and he'll be taking us through the first part of today. Over to you, Corey. You're on mute.
Sorry for that. Sorry for that. Thanks a lot. My name is Corey, solutions architect at Amini, but I have a background in geospatial data science. So I'm going to start off this webinar, and as you've been told, it's about processing Earth observation data for machine learning. So at the end of the day, you know that we have two broad categorization of geospatial data. We have raster data, we have vector data. And I think these are things that you've already gone through or you were taken through in the previous webinar. So I just want to start with, what is the ecosystem? What are some of the tools that we use in doing this geospatial data analysis? What are some of the tools that we use to process raster and vector data? So I have my data. I have my data paths that I've linked to my drive and some to the GitHub repository. It's a public GitHub repository. And when you get this notebook, you're able to get access to it. And I've also given you some instructions on how you're able to download some of the data that, for example, the raster data, that is the Sentinel-2 data, and even the shapefile data. And also we have some other data that is from ECAS. You're able to download it from the Google Drive. So let's start. So the first tool that we'll talk about, or the library that we'll talk about, is GDAL. This is a geospatial data abstraction library, and it's an open source library, and it's used to read, write, and process these geospatial data. Here we talk about raster and vector data formats. So, for example, for raster data, we have GeoTIFF. We also have other formats like NetCDF and all that. And for vector data, we have shapefiles, we have JSON, we have well-known text or WKT that is always in form of CSV. So, what does this library do? So, first of all, it does metadata extraction. When we talk about metadata, we always say that it's data about the data, just trying to describe the data itself. So when you want to understand the data better, there's some information, and that is the metadata. So reading and writing raster and vector data. So how do you read these multispectral raster image, or how do you read these shapefiles? So GDAL is the library for that. Then we have the projection. We have different projections on the surface of the Earth. And when you're working with your data, whether raster or vector data, there is a need for you to convert from one projection to another. So GDAL helps in this, and also clipping of data sets. So we'll talk about that. So we have the second one, which is Rasterio, which is typically built on top of GDAL. It does the same things, but it simplifies the tasks like resampling and all those stuff that we've been talking about in masking. Some of the functionalities are just the same as GDAL, but this is now for raster data. So it's reading and writing raster files, extracting metadata, and masking rasters using vector geometries. So I won't run this file because I've already run it, but you can run this file if you don't have some of these libraries installed. So I'll import Rasterio as Rio, and when I'll open the image. Rio is the Rasterio for raster data. So I'll open the image and as SRC. Then the first thing is I'll want to access the metadata. So then I'll print the metadata, and when I run this file, this is what you get. Then I'll show, or I'll show the image, as you can see here. So for the metadata, we have different types of metadata. The driver, there is the GDAL driver. This is GT. We have the type of the data, which is float 32, because at the end of the day, you understand that satellite imagery is just basically it's an array. It's an array of numbers. At the end of the day, it's an array of numbers. We'll be able to talk more about that. Then talk about the width and the height. These are the pixels of the width and the height, which is 657 and 608. And these are sentinel to multispectral imagery. So it means that it has a 10 meters spatial resolution. And when we see the count here we're talking about the channels or the bands. So it has about 19 channels or bands. What I always use when I try to explain in terms of geospatial, I always use the normal imagery that we always take with our phones. The normal images that we always take with our phones is still multispectral, but it only has 3 bands. That is the red, green, and the blue. But for the multispectral, it has around 19, including the RGB and other channels. Another very important metadata that it's about the transform, the affine. This metadata is used to help in what is called choosing a georeferencing. It gives images the geographic aspect. So when you use the affine or the transform metadata, it helps you transform your data and give it now the geographic aspect of it. So when I run show, you're able to see the image here. So that is about Rasterio. Let's go to Geopandas. Now, we've come from the raster data. Now, let's go to, just a minute. Now, let's go to vector data. So just Geopandas is just an extension of Pandas, and it allows spatial operations on geometric data. And it integrates seamlessly with the other libraries like matplotlib. So it's used for loading and manipulating vector data for spatial joins, also for geometric operations like buffering and intersection. Buffering is where you have a point and you want to increase or you want to buffer around that point. So Geopandas does that very well for you. So this is just an example. So we have different formats of vector data. We have JSON, we have JSON formats, we have shapefiles, we have WKT. So when you use either, this is what you get. This is for JSON. I'm able to do the one for shapefile. You'll still get the same, and if even for WKT, you'll still get the same. So Geopandas helps, in doing such kind of operations. Now let's go to X arrays. So we've talked about raster, Rasterio. We've talked about Geopandas. Let's now go and talk about X arrays. So a number is always used to do, always used to manipulate numbers and arrays. But when it comes to X arrays, this is designed for working with multi-dimensional labeled arrays. And it's very ideal for handling satellite imagery data. Why? Because when you look at satellite imagery data, it's a multidimensional array. It has, the height, the width, then it has the bands. And to add on to that, now comes the real X-array, which is an extension of X-array for raster data, and it is used now to process the satellite imagery. Now, for satellite imagery, as I talked to, as I said just before, is it has the X, Y, and the Z aspects. That is the height, the width, and also the bands. But also it has the aspect of time, because when you have sentinel satellites going over, it comes back to the same place a number of times, and you're able now to get time series data. So how would you work with this time series data? Now you have the X, the Y, and the bands, but for different times, for time series. So X-arrays is very real X-array and X-arrays are very key library or key libraries that are used now to manipulate satellite imagery more so, and most importantly, time series satellite data. So you import your libraries, then you open your image. I have the image already in my environment. And when you run this is what you get. So you see, we have the X and the Y, right? Then we have the band. We have like 19 bands. That is in the Sentinel-2 multispectral imagery. But in this case, it was just one image for now. But Collins, or the next speaker, will talk more about now the time series aspect of it. So this is what you're able to see, the X, Y, and the bands, but only for one date or one timestamp. So from this, so how do we now manipulate these geospatial data using radio X-ray, right? So we can even plot, and you can see here, this is the data sets or DS. You're able to get the data as the X-rays. Then you're able now to from the DS, you're able to get the different band. For the red band, you can even get for the blue band and plot that band. So there are some you're able to check on the real X-ray. I'll be able to leave a link for the documentation of real X-ray or X-rays, so that you can be able to choose any band and visualize the band visualize the band. For example, for these, we are visualizing the red band. You can be able to see it as visualize the red band for the image that I had. I can be able, yeah. So you can even compute NDVI. NDVI is a ratio between the near infrared and the red bands, and they always try to look at the vigor in the vegetation, just trying to understand is it healthy or not healthy? Does it have higher NDVI or lower NDVI or something of the sort? So you can also compute the NDVI for the entire image, and this is what you get. And of course, the higher you go, it means the healthier the vegetation is. So we also have resampling, but I'll talk about resampling, then I'll come back there. So let's now go to the basics. So we've talked about four. So we started with GDAL. Then we went to Rasterio, then we went to Geopandas, then Rasterio. So let's just go through the basic preprocessing workflows. So the first thing is data ingestion. When you have when you're starting your processing, or the first thing that you do is you ingest the data. And I think we had already done that. But Collins will also show you how you're able now to get these data from the different data sources that we get these satellite imagery from. So for me, I have it in the Colab environment. So I just load the raster data as I did earlier. So the second thing that I just talked about it a bit was the reprojection. So reprojection is just about putting all the data sets into one common coordinate reference system. because some of the data that we always get, whether it is raster data, whether it is vector data, some of them come and they are at different coordinate reference systems. So for you to have like accurate spatial analysis, then you need to put them into a common CRS. So the first thing is first check which CRS is it. For this, it is EPSG R4326. This is the common geographic coordinate system. It is used worldwide. It's based on lat and long, and it is not projected. Then now I want to reproject this GDF now into maybe UTM. And this is, as you can see, this is UTM 37 in zone 37 and in the northern hemisphere. So when you want to reproject, this is the code snippet that you use to do the reprojection. So you just take your for this, we are using vector data. So you take your geo data frame, which is GDF, then you transform it into the coordinate reference system that you want to transform it. For us, you need to transform it to 32637. So when you transform it and then you print the coordinate reference system, you get that now it has already been reprojected into the one that you wanted. Clipping is very important because you have a sentinel imagery or maybe a tile of sentinel imagery. They're always very huge, and maybe maybe you're just interested in some small patch. You have a small area of interest. Let's say just a farm. So what do you do? So what you do here is you click into the area of interest so that you reduce, doing a lot of computations on other areas that you're not interested in. So Rasterio has a way of doing it, and it has this function here. It's called the mask. So first of all, when you're masking, when you're clipping, it means that you're using a vector data, let's say a polygon, and you're using that to mask or to clip a raster data. So so first you load your vector data, and then from there you clip the raster data using the vector data that you've loaded. So this is what it will do. It will take the image, then it will get, this is the metadata, copy the metadata. Then the metadata now will be used in writing out whatever has been clipped. So we talked earlier about GDAL or Rasterio being used to read and also write. So at the end of the day, after you clip, you also need to write. You also need to write. For this, you save the clipped raster, and when you save the clipped raster, you're using the metadata. You're copying the metadata from the raster data, right? That you're clipping from, and using it on this clipped raster. So that is what you do. So for this, you can also see that is before clipping. This was the whole the whole image. After clipping, you can able to clip a very small area. It was somewhere around yes. So that is a very small area. So you use the vector data, that is the polygon, to be able to clip the raster image. So you can be able to take this raster image here and be able now to do your zonal statistics or to do statistics or to analyze that raster image. Then we have resampling. So here we are dealing with alignment of data sets that have different spatial resolutions. Sorry for the typo. Have different spatial resolutions. So when you talk about Sentinel-2 imagery, Sentinel-2 imagery has a spatial resolution of 10 meters. And maybe you want to do an analysis and you also want to use Landsat data. Maybe there is a way you want to fuse the data from the two satellite sources. So what do you do? What you need to do is you need to resample your data so that both data sets have the same spatial resolution, and that is what resampling does. So Rasterio also has a function that does resampling. So you can use that function to do resampling. So this code snippet does the same. For this, what I decided to do is after I decided to clip like a portion of this data set because it was big for visual purposes, so that you're able to see. So I clipped a portion of it. Then after that, after I clipped, I was able to resample it using the resampling function from Rasterio. And what you get here is you get the clipped. Uh, this is the this is the this is the image just before resampling. You can see how it is. Then the image after resampling. So the image after the sampling is a when you have a closer look at it, you see that it is more coarse. Why? Because the resampling, what the resampling did, it took a number of pixels from this image and put it as one pixel. And that is why you see that the spatial resolution of this second image has increased more than the first one. So it's more blurred than the first one. So that is what the sampling does. It enables you now to put different data sets that you want to do your analysis into one spatial resolution for you to ease your analysis journey. So you can see that before sampling, we had 3 bands because I only chose 3 bands here. I only chose the RGB. I only chose the RGB. So it has 3 bands. It has 152 pixels and 164 pixels. That is before sampling. But after sampling, we get that this is 3. Then it has 76 pixels and 82 pixels. So it means that the number of pixels have reduced, but also the image has become a bit coarse. So we have like quality assurance methods. When you're working with satellite data, there are a lot of noise that always comes with satellite data, and also the vector data that we always collect. So how do we try and do what? How do we try and make sure that the data that we have is good for modeling or for machine learning? So first of all, the thing we do some visual inspections. Sometimes you can be able to see an image and see that there are some parts of that image that maybe because of what is called cloud masking that does not have some parts does not it has some gaps because of maybe masking or something with the solid cloud masking. Then we can use statistical checks. We can also use outliers detection like histograms. And for these, uh, and Collins will talk about this. When you have time series data, right? When you have time series data, you can be able to do what is called gap filling, so that those areas that have gaps are able to be are filled, and you can also do smoothing. Because we have some other pixels that have a very high or the outliers, so we need to smoothen. And those are just some post-processing activities or tasks that we do. We can also do some vegetative tests to make sure that this is just like a validation and quality assurance methodologies. We can even check for no data values, check if our data, like the image that we had, if it had no data, but no, our image had it did not have any gaps. You can even check. You can even check whether the vector data. So whether the vector data that we had have some invalid geometries, maybe some of the lines in the polygons are crisscrossing each other and all that. So from the initial data that we had, that is from the data, we had these, just a minute. We had around 13,000, 1,353 datasets in this shapefile. We have records around 1,000, but when you check the invalid geometries, you only have around 23 invalid. geometries. So we're able to plot one of the invalid geometry, and you can be able to see these are polygon, yes, but it is in an invalid polygon. Why? Because when you see this polygon, you see that it is crisscrossing. You see some of the lines in the polygons are crisscrossing each other and getting this. So that is an invalid. So you can be able also to do that for quality assurance purposes. You can even plot a histogram of your raster data. You can say that I first want to check, I want to compute the NDVI. I want to compute the NDVI, then after computing the NDVI, I want to check the histogram of the NDVI to check whether there are some outliers. So those are some of the statistical, when I run this, we just give me the sum. So you're able to plot the NDVI, this is the NDVI, then you're even able to check if there are any kind of inconsistencies or outliers from the histogram. So this was just like an introduction to processing observation data, just to get you through some of the basic the ecosystem that we use in the geospatial data analysis. So if you have any questions for me, maybe you can write them down in the comments or after Collins finishes his presentation. So I'll hand it over now to Collins. Thank you.
Thank you so much, Corey. I will try to share my screen. Okay. So I hope you can see my screen.
Yes, we can see your screen.
All right, awesome. So I will pick it up from Corey where he's left. So my name is Collins. I am a geospatial data scientist. I have a background in art science like EARTH. I have a lot of interest in hydrology, water resource management, and also geology and mineralogy. So this talk will specifically be addressing the X-array or the time series data acquisition. So we pick it up from last time where we did some samples. If at all you were able to follow the first notebook that we shared. So we have like these libraries that we are using. And this time around, the only library we are adding is Planetary Computer, which is some service that is being offered by Microsoft. Initially, it used to offer compute, but currently they disabled the compute. They only have like datasets. So you can use their stack URL to get datasets. So initially, in the last session, we used what we call the Element 84, which has Sentinel-2 datasets. Our Planetary Computer, in comparison, has a lot of datasets that you can use. And if you just explore their catalog, there are a number of datasets that you can already start to use. You have Landsat, you have MODIS, you have Sentinel-1, Sentinel-2, you have climatical datasets, a lot of datasets. So if you are interested in data sources, then you have like Planetary Computer as your to-go guy. The next part is, so I will try to go through some of the libraries we're using. So I've talked about the Planetary Computer, which is just some sort of data provider that we're using in this particular scenario. There is PyStack. I think we already used that in the last tutorial or session. We have Rasterio, Geopandas, which Corey has evidently dealt with. And then we have Rio X-array, which is also an extension of X-array that has like the Rio part, which is the geospatial side. So here we're just importing some of those libraries. And then the next part, so initially we handled most of the things like just writing variables, but in programming, usually say if you're going to use it more than once, write a function. If you're using it more than so many times, then write a class. So that's why sort of we try to write some functions. So this is initially what we're using to handle the feature collection to ensure that it's in the format that the stack or the stack library expects. And here we decided to write the stack items into a function such that if we want to get more than one data set from, for example, planetary computer, we want to get data set from element 84, we want to get data set from any other place that is having stack URL, then we can already start to use that. So there's something unique about the planetary computer. If you want to use their data sets, you have to some sort of sign. So this is like a PC which signs that particular data set so that you can be able to use it. So if you don't do the signage, then you might not be able to access the data sets. So we have our area of interest, which we are going to now use to fetch the data sets. And then after this, so Corey has already talked about the geospatial data library, which is the Geopandas, where you are reading from different data formats. And if you want to read, for example, from a feature collection, this is how you read from it. And you have additional use cases or operations that you can do. So in this case, we are just getting the bounding box, which is just some sort of the extent of the data sets. So this bounding box, we'll use it somewhere to help us to limit the area of our images that we are going to use to create like the data array. So in this case, we are using our function, and we put the URL for the stack planetary computer. And then we want this particular collection, which is Sentinel-2, the same collection we used last time. And then we are using our area of interest, which is the feature collection. And we are assigning the dates that we want to use. So here we are taking a longer time, which is 2021, the first month, which is January, to the 6th month, which is like 6 months of data. We have a couple of items. So remember, in our function, we limited the number of items to 10. So this one also affects the amount of data we are going to receive. So for the purposes of this particular session, we decided to limit it so that we are able to run the scenario quite quickly, so that if you jump on it, you can be able to sort of get the hang of it a bit faster. So inside, we are using StackStack. StackStack is a library that is able to create an XArray data array and reproject it using the CRS, which is the coordinate reference system, and also bound or clip it to that area of interest that we want. And in this case, you're using the bounding box as our guiding role. And in that case, it requires that bounding box be in a tuple format. So we convert the bounding box that we created up there, which is an array, to a tuple. And then there is resolution in degrees. So basically, we just did a conversion of the 10-meter resolution to decimal degrees. So decimal degrees is like a unit of measurement that is used in the geospatial side. So once we do this, StackStack is able to create for us a Sentinel-2 data array with a couple of bands, which are quite many. So if we check here, we have AOT, we have band 1, band 2, band 3. And in the previous lesson or session, we were able to discuss how to check the metadata from the stack catalog or a stack item. So basically, be sure to consult that notebook, be able to understand the wavelengths for each band and any other information. So basically, here we're just trying to show you how many bands we have, which is about 17 bands. And from here, we want to do preprocessing. So preprocessing steps usually are helpful to ensure that when you have your data set, you can be able to remove or clean some noise. And one of the issues that we have with satellite data is cloud cover. So usually each satellite data, you have to look at the documentation. There's a specific band that is assigned to help you to cloud mask those images or remove clouds from those images. So in this case, these are the values that we are using. And this is on the ESA. There's a bank called SCL, SEL, which is used to do that. So down here, we just have a function that is helping us to do the cloud masking or to create the cloud mask. And then once we create the cloud mask, down here, we are able to now continue with the pre-processing step. So the first pre-processing step is to do cloud masking. Remember, when you get this data, when you acquire this data from a planetary computer, be sure to read some of the documentation about to what level has this data been processed. So you'll have scenario where the data has been processed, the atmospheric correction has been done, the geometric correction has been done, and maybe you just need to do the cloud masking. So we apply the cloud mask and we do the scaling of the data so that we are able to achieve a more cleaner data set. And so here we just group the data by band, and we check the first band. And if we look at our data set now, it's now cloud-free, or we have removed some of the clouds. Remember, when you remove the cloud from the image, you now create holes inside the image. So it's a cleaning process. And that's where Corey was mentioning we do something called gap filling. So gap filling is a process where you interpolate from the neighboring pixels and the before and after pixels of that image. So take an example. If you have an image that was captured yesterday, and then there was an image that was captured last month for the same location, and a specific pixel has been cloud masked, meaning it was a cloud pixel. So you look at the neighboring pixel, and you also look at the before and after pixel for you to be able to predict which kind of pixel can this be. So currently we have like methods that have already been, the traditional methods that are used to do the cloud masking. But I believe that some of these problems can be handled using machine learning. So that's why you as experts in the field, you can be able to develop certain algorithms that can be able to sort of predict that pixel. And we can be able to take some ground of observations to actually understand whether the accuracy is high or not. So this cloud mask data array has a couple of bands, I think around 17 bands, and it have the time dimension. So this is what we're talking about, time series. So we have around 21 images for this particular 21 timestamps of 18. So think of it like this: you have 18 bands, and these 18 bands are 21 times. So each timestamp has 21. Each timestamp has 18 bands, and then the Y and X are basically the coordinates. So, and of course, usually all data sets will have some indices. So in that case, you have X and Y, and you also have the band. So you can select by X and Y. You can also select by band. So now we usually prefer to work with XRA data sets when you're preparing data for machine learning purposes. And in that case, we want to sort of filter some of these data sets. I think is part of the processes for machine learning. And it also depends on your area of interest. So in this case, we want just to select a few bands. So here we are talking about blue, green, red, near infrared, SWIR 1, 16, SWIR 22. And once we select this, we want to convert this data set to an XRA data set, and we are using the dimension band to create that. So after we do that, we end up with data variables. In this case, it's an XRA data set, and it has the data variables, which is blue, green, red, near infrared. So we have reduced the number of bands from the 17 bands it was having to now just how many bands? 1, 2, 3, 4, 5, 6, 7, 8 bands. So in this scenario, we can still do further filtering. So it's not only at this level in this XRA data array that we can filter. Even when it's XRA data set, we can still do filtering. So we can select just one band. If you select just one band, we'll go back to XRA data array, which will have only the blue band. So this was supposed to be blue. I guess we have to change it. Have to change this. Of course, when we share the notebook, it will be a bit more cleaner. And then we can still select more than one band using this particular methodology. So you just need two square brackets. And in this case, you'll end up with the X-array data set. So at any given point of your processing, you can still do selections of the band. And you can also add or merge add a band inside your data set. So you are still able to add and remove. So we want to visualize one of the data sets. In this case, we can visualize the blue band, and we are taking the Sentinel-2 data set. We are doing an ICEL, which is a selection. And then we want to look at the the third. The array start from 0. So the third item inside that array. And we are plotting the blue, and we are using this particular CMAP or color map controller to do the plotting. And we are able to visualize this data set. So let's dive into time series analysis or time series. So this one, I'll take a description from Python recepts. Wow, the spelling is not good. Python recipe for earth sciences. So time series analysis are methods that investigate data sequences as a function of time. They usually look at long-term trends, which could be periodic, cyclic, dynamic, and the climate person will tell you can be chaotic. So you have the random aspect and the stochastic aspect, and some are also deterministic. So usually, but in most cases, when you're dealing with a complex earth, it might be a bit difficult to have a deterministic outcome. But usually most of these systems can be predicted. So I would recommend that book as part of the reference if you are more interested in learning science and data sets, how to work with certain data sets. So next, we want to do like a time series plot of a specific point. So we take a latitude and longitude of this particular point, and we want to sort of plot this point to understand the time series aspect of that particular point. So in this case, as Corey has mentioned, you can do for a point, you can also do for an area, for a bigger area, because a point or a polygon is just a collection of many points. So we want to calculate an index, which is NDVI, is a widely used index. So we chose it because it's a bit widely used, but you can also use any other index that you want. You can also create your own index to solve a specific problem. So here we just compute an index. And remember, this is a time series data set. So when we compute this index, we're actually computing an index for the entire time series, which were 21 timestamps. So, and this process now down here, we want to do like a time series for this particular point. So we rename that particular data point to NDVI, and then we use .interp. .interp is like intercepts. It's a short form for intercepts. And then we take the X point, the X coordinate and the Y coordinate, and then we compute that. So we end up with an array of different values ranging from, so NDVI usually from -1 to 1. So here we have like values, the first timestamp is 31, or 0.31. We have the last value, which is 0.48 something. So this is like, can be used for phenological studies if you want to understand a specific crop, or you want to understand the time series evolution of a specific subject. So here we want to plot that NDVI for that particular time series object. And you can be able to see that we have the NDVI going down and going up. And so we can be able to start to understand which characteristic of object can this be? Which characteristic of this object can this be? So usually this is a very important thing for data scientists. This is what we call data exploration. And the next part, we'll be looking into data aggregation. So data aggregation usually is very important in terms of reducing the number of the observations. So for example, we have 21 observations for that 6 months. And then because usually we have like one at the equator, you have at least one image every 6 days. And because of cloud cover and stuff, so you want to sort of compact this data so that you can remove the clouds, you can do the gap filling. So depending with your use case, you can choose to do data aggregation or reduction of data sets. And I think that is a subject that is usually in statistics. So reduction of dimensions, among other issues. So usually there's a native way inside the X-array library, which is the resample component. So resampling is not only used for the reduction of resolution, it's also used in reduction of or a reduction of the amount of data that you have of observation. So you can do a mean. And in this case, we want to do a monthly reduction. So we don't want to have a 21 observations. We just want to have like the number of observations to be reduced to be a monthly time series. And you can also consult the pandas documentation, which is usually showing you like the different streams that you can use to sort of reduce your data. So you have the monthly end. So this is the end of the month. You have semi-month, you have a business month, you have a lot of them. And then you have like even bi-weekly and weekly. So going back to our notebook, we now see that our data has been reduced to now 6 observations. The X and Y remain the same. And now we are ready to plot our data and look and see how it looks. So we follow the same process. We do the interception of X and Y and we compute that. And we can be able to see our data set has like the 6, the array has already been created for us. So here, again, if we look at our data set, we have this particular showdown, and you can see the way it has evolved. So it started at 0.3, it went down a bit, it went up, and then down a bit like this. So if you give this data to Corey, Corey can be able to give a very good story of what that would be. And that would be, let's say, a story for another day. So next, we want to try and prepare these data sets to a format that can be consumed by a machine learning model. And in this case, we can convert this data to a Dask data frame. Why a Dask data frame? Because it can be able to handle data much easier, that the data that cannot fit into memory, it can be able to help us to export that data, and it will create like some files for us. So you may also consider doing it as a GeoTIFF. You export them as images, or as an HCDF format, which Corey has shown before. And in this case, we can be able to inspect the head of this particular data set, and you will see that you have a couple of columns that you might not need. You might as well discard them, and you have the bands and their values. So you have the blue, the green, the red, the infrared, and SWIR 16 and SWIR 22, and all of them have values. And we can as well export this data frame to a CSV. You can do a Parquet and any other operation that you usually do with a Pandas data frame, you can already do with this particular kind of data set. So I think I'm getting closer to finish. So you have further exploration. So basically 1 hour session could not fit to do like a lot of stuff. So there are other things that we would recommend. So look into the univariate multivariate data processing, the applications in art sciences problems. There's a very important thing called the signal processing for art sciences. So usually signal processing includes like techniques to manipulate signal in order to minimize the effects of noise, and also correcting all kinds of unwanted distortions. So there are usually a lot of distortions when it comes to satellite data. If you look at the atmospheric conditions, for example, there are days where there's a lot of humidity. There are days that there's dust. There are days that there's clouds. So signal processing would be very important to sort of understand so that you can be able to handle some of these data sets. So there is also analyzing direction data. So direction data, think of it as movements. So for example, a river moves in a specific direction. So how exactly do you analyze this? So this is like sort of a physics-informed data analysis that you want to do. And the other thing is zonal statistic. I think this should have been up because we have done some form of the zonal statistics, if you ask me. So this is because we have analyzed for a specific point, but zonal statistics you can also do for a country, for a region, for any other specific location. And then the other thing is to combining data from different data sources. So for example, here we have only looked at Sentinel-2. There are data sets that we have shown you on different catalogs. For example, Element84 has data from Landsat, Sentinel-2, Sentinel-1. Our planetary computer has data sets including temperature from CHIPS, GPCC. There are climatological data sets. You have even population data sets, water layers. You have digital elevation models. How do you combine these data sets into one so that you can use that for analysis or machine learning stuff? Self-challenges. So we encourage any of you who might have some time to learn about active sensors. So active sensors is usually Sentinel-1. These are radar penetrating sensors. So for example, they can be able to penetrate to clouds. So usually they are not very affected by cloud cover, and they are very useful for biomass mapping. Steve Fasek in the first session spoke at length about this. So if you are able to look at it can take images even at night. So it's a very important sensor when it comes to Earth observation. And then look into Stack API. So use Stack API to acquire the active sensor, which is Sentinel-1, preprocessed to X-ray. So in this case, you look at speckle vectoring. So there are a couple of methods that are used to process Sentinel-1 data sets so that you can be able to use it. And it can also be used for deformation mapping. So if you're looking at disasters such as landslides, you're looking at places that are experiencing overdrawing of water, like over pumping of groundwater, and these areas are sinking. So you can be able to use that. And some applications can be like prediction of where the next landslide will occur, the next earthquake can occur. So Sentinel-1 active sensor is a very important one. Also, there are other active sensors, some which are not open source. The other challenge, so it's just like the challenge is following step by step, is to combine this data into one data and handle the depths. For example, the observation of Sentinel-1 and Sentinel-2 may not overlap or be the same day. So you might want to kind of handle that so that they can be able to get the closest dates so that they can share the dates so that you can have one data set for machine learning purposes. As I finish, I have been finishing for the last 10 minutes. So there is learning resources. So the internet, of course, is the largest learning resource. Sessions like these are also very useful. And also there is the Earth Observation College, which has a couple of trainings, and also there are certificates that they offer once you finish a specific course. It has from the fundamentals of remote sensing, radar remote sensing, you have multispectral or hyperspectral remote sensing, among other things that you might find useful, and even downstream applications. Also, they have some sort of fundamentals of machine learning for Earth observation or Earth sciences. I want to end from this point, and I welcome any questions. Happy to take them on. Thank you.
Thank you so much, Collins. We've already got our first question from Paul. Paul, do you want to unmute yourself?
Yes, thank you so much, Collins and Corey. So my question is, it's going to be somehow related to what we have discussed. And the question goes to Collins. So like I have a question, like one time while I was preprocessing data, so I got the data from Google Thinking.
Yeah.
So like now you find that the data, for example, of NDVI, you have collected images from it. For NDVI, you have preprocessed well, you have removed the cloud and other that may be bringing the distortions with the image. Now here was a scenario of that the person I was with, like when preprocessing to take out the NDVI values, he wanted to stack the images. Because now, for example, for Sentinel-2 has a revisit time of 2 to 4 days around. So you find that if each day it collects. So when you look at that temporal resolution, and now like, for example, you want to take monthly. So the image was going to be like, it was going to coordinate for that. For example, if it takes 2 days, it's going to have 15 images. So it will what? For example, I think to have 1 image for each month. Now, the problem, like we resampled and we stuck the image and like, for example, because the time frame was supposed to be for 3 months for each image. So remember, after calculating NDVI, it becomes 1. The channel becomes 1. Yes. So, and you find like we found ourselves having like 3 channels in 1 image since it was stacked. Now, the issue was with extracting that NDVI from the image because the person was talking about using CNN to extract that information. And like in your code, I saw somewhere, yes, exactly there. So I was wondering like how that happens because the person was like, we have to use CNN to extract the NDVI from that point. So and I was like, how can this be? Because now basing on that image is stacked with 3 channels for NDVI, for example, for 3 months. So how will this look like if that happens? If I use this code, for example?
A very good question. So usually with Google Earth Engine, yes, there are a couple of ways that you can extract like time series information using, for example, some reduce regions functions that are already natively inside of Google Earth Engine. But if you are to use this code, then it means that if you want the entire data set, like this one is like the entire data set for the data frame. So you're converting all the images into the values. And then you will have the X and Y forming parts of our data. So it will be a very huge data set that you can already use for your purposes. And if you want to do, for example, a zonal statistics for a specific location, then you can look into how to sort of use like something like interpolates XY. You can also interpolate using a geometry or a bounding box to generate that particular data set. So with this kind of code, already you have a starter pack of how to generate that time series information. And also, if you were to look into how we did the monthly, this monthly NDVI data, where we resampled it to monthly. So you already have an out-of-the-box solution to that problem. So for example, if you want a monthly resampled, so you already have like a monthly data set. And with this monthly data set, you can already export this data. You can already do an interpolation or zonal statistics using a point, a polygon, or a bounding box to generate that particular data format. And you can use it for any other analysis that you want to use. Yeah, so unless you want like a specific solution that is working with Google Earth Engine, then maybe we might want to understand with the colleagues from Zindi and also my boss at Amini if that is possible, and then we can do that. Yeah, I hope I have answered your question.
Thank you so much. Anything else? I think we should be interacting.
All right, no worries. Yeah, thank you.
Thank you, Paul. Next question goes to Alan. Do you want to unmute yourself?
Hi, can you hear me?
Yes, we can.
Hello, yes.
When you're talking about the monthly data, you see
Yes.
we have a raster that is has a dimension, right? That has a 2x2 dimension, and then each raster file has like is contained of a different band. So if you have
Yes.
this raster as for 6 months, how is the dimension of this raster of this data set going to be like?
Okay. So think of it as, so you have, it takes each month and reduces each month into one image. And this one image has the number of bands that were original in the original. So think of it like it depends with how you take it. So here you can use a mean, you can use a median, you can use a sum, and all the mathematical principles that are there in terms of dimensionality reduction. So what changes here is just the time of the time dimension that is reducing, but the bands are remaining the same. Yeah. So here you look at the shape, which is 6, 155 to 20, and then up here, let's see if we showed any of the shape. Yeah. So here you have 21, like that. So I don't know if I correctly answered your question. Yeah.
So like for 1 month is going to be one raster with different bands.
Yes, exactly. This is going
And
to be
then
one. So yes, continue.
how is it going to look like for 6 months? Because if 1 month is one raster, and it's how many bands are we dealing with?
Okay. So you have 6 times. So initially we had 21 bands, right? And then we filtered out some of those bands. So if we were to do a reduction of, so here, let's start, please. So here, we were doing a reduction of only the, what is that reduction? I have to check it out. It's here. So here we only did the resample for the NDVI only, but we can also do reduction for the entire data set. So we can say Sentinel-2, 6 months, maybe something like that, blah, blah, blah. So it will be each image with the native. So if we were to work with the 8 bands that we first of all filtered, let's just work with all the bands. So these 16 bands will be like, it will be 17 bands times 6. So we're working with around 17 times 6. Yeah. So that would be like the number of bands that we'll have. So each month we'll have one image with 17 bands. If we were to do a dimension reduction, a monthly reduction for each. Yes.
Okay, I get it. So it's like you're dealing with one band for 1 month, and then it is a stack for like 6 months, right?
We are dealing with
NDVI.
okay. Yeah, we're dealing with,
In
let's
this
say,
case.
so in this case, you have AOT, all this in one image. So for one time, so let's say January, you have that image stuck with 17 bands. February, one image stuck with 17 bands. March, like that until June. And if you were looking in the original data sets, you have the time steps, which were 21 time steps. So each time step has 17 bands. Yes.
Okay. And then if I can see a time series analysis, is it the complete file, or did you do the training for the time series in a different file?
No, it's the entire file here. It's not different. Yeah.
So like, did you train a model to predict the time ahead, or what happened at the end?
No, these are just observations. So we haven't, okay. So for the training part, I think that will be the next session, which now Clinton will handle that. So this is basically just the pre-processing steps, preparation of data for machine learning application. Yeah.
Okay. Thank you.
Yeah. Thank you, sir.
Thank you, Alan. Does Dennis want to go?
Thanks, Collins and Corey for that presentation. So I think my question is for when you're calculating, or rather calculating the time series for NDVI, for example,
Yes.
it does
Yes.
calculate the average for the whole field per given time, right?
The time series. So if you're doing like that zonal statistics that we did, it takes that specific point, which is this X and Y, and that creates for us the values for that. If you're asking about calculation of NDVI for the entire data set without using the interpolation bit, then it does calculate NDVI for the entire image using the specified bands that we need. So in this case, red and infrared and near infrared. Yeah. Go on. Hello?
Yeah. That's I didn't see the X and Y that you picked for
Sorry.
the time series. I thought you calculated the whole raster.
Oh, yes, you can also do that. If you want to
Yeah.
do like a dimensionality reduction for the entire raster, you can also do that and create like a mean for the entire data sets and get like a time series for the entire image. Yeah, so if you want to just, that would be like the entire image, you get a mean of each point. Yes.
Oh, okay, thank you.
That's also possible. You're welcome.
We've got time for one more question. Does anyone want to raise their hand? Or you can put it in the chat. Yes, Paul, back to you.
Plus now, then like leave alone NDVI. What if I want to look for other indices like the normalized difference water index? I want to look at the chlorophyll index. Like, can I be able to use this same code and I get those indices?
Yes, so in that case, you'll just be writing the formula and calculate those indices. So when on the final version of this code, maybe you might type in the chat which kind of indices you want so that we can just maybe write like the formulas for those. And then we will add like a few indices, non-indices or common indices that you can use. And then we can also like still be able to write those formulas and generate them. Yeah. And also maybe we can add how to add that index into the original data set so that you can have like a data set with an added band into it. Yeah. I hope I have answered your question. Yes, awesome. NDWI, CCI, and LAI. All right, awesome. That one has been noted, yes.
Okay, we're going to wrap up the webinar there, and Collins is going to update his notebook so you can find out the NWVI and all those other indices. These notebooks will be available on Zindi tomorrow. So if you just go to the Amini Canopy or Crop Challenge, I'm putting the link in the chat right now. You can sign up and you can start playing with these indices. The data's already there. You can maybe even start pipelining, which is our next webinar in 2 weeks' time. I want to give a special thank you to Corey and Collins. I'm sure we could all listen to them talk for hours, but thank you so much for attending this webinar. As a reminder, if you attend webinar 1, 2, and 3, there are 20 mentorship spots open. And that is to have a session with someone from Amini or someone from Zindi, specifically around Earth observation data. So please do attend the next one. Best regards and thank you so much. I'm going to end the recording now.
Bye.
Bye. Thank you.
Thank you.